Have you ever stopped to wonder why some things are super hard and others are, well, soft? Or why some things conduct electricity and others just don't? The answer is way simpler and honestly, way more profound than you might think. See, it's not just about what something is made of, it's about how it's all put together. Today, we're going to pull back the curtain and see how the secret architecture of atoms defines literally everything around us.
So let's kick things off with a bit of a puzzle. On one hand, you have a diamond, the hardest natural substance known to man. On the other, you have graphite, the soft, flaky stuff inside your pencil. Now, here's the wild part. They are chemically identical. Both are 100% pure carbon. So what gives? How can the exact same atom build two materials that are complete opposites? That's the mystery we're diving into right now. There's actually a scientific name for this whole phenomenon: allotropes. It's just a fancy word for different solid versions of the very same element. Diamond and graphite, they're the most famous allotropes of carbon, but they're not the only ones. The fact that the same element can have such different personalities, well, that tells us we need to look a lot closer, much, much closer. All right, to crack this case, we have to play detective, but on an atomic scale. And our very first clue is understanding the invisible force that holds atoms together, which we call chemical bonds. Think of it as atomic glue. The type of glue and how it's used, that's the key to everything. That's right. It all boils down to the electrons, those tiny little particles just buzzing around the nucleus of every single atom. The way they're shared, or even passed from one atom to another, that's what determines the strength and the shape of the connections they make. So let's get into the main types of this atomic glue. First up, we've got the covalent bond. The best way to think about this one is like a really firm, cooperative handshake between two atoms. They each put an electron into the middle, and they agree to share that pair. This sharing creates a super strong, really stable link, and it's the main way that non-metal atoms, like our friend carbon, like to connect. Okay, next is the ionic bond. This isn't so much a handshake, it's more of a give and take. One atom completely hands over an electron to another. This little exchange creates a positive charge on one and a negative charge on the other. And you know what they say about opposites. They attract. They snap together into this rigid crystalline structure we call a lattice. And finally, there is the metallic bond. Now this one is pretty unique. I want you to picture a whole neighborhood of positive metal ions, all sitting in their fixed spats. But their outermost electrons, they're not tied down to any single atom. Instead, they form this incredible sea of electrons that are totally free to just flow throughout the entire structure. And that sea, by the way, is exactly why metals are such great conductors of electricity and heat. So we have our types of glue: covalent, ionic, and metallic. But a single drop of glue isn't a skyscraper, right? So now let's zoom out and see how these individual bonds can build the massive, giant structures that we can actually see and touch in the real world. So when countless atoms bond together, they form what we call giant structures. And they pretty much fall into three main buckets, which line up perfectly with the bonds we just talked about. You've got your giant ionic lattices, like regular old table salt. You have giant metallic structures, like a hunk of copper. And then you have the giant molecular or covalent structures. And this is where we find the answer to our whole diamond and graphite mystery. See, both of them are giant molecular structures, built completely out of those strong covalent bonds. So if they use the same atoms and the same type of bond, how on earth can they be so different? Well, the final piece of the puzzle, it's the architecture. Okay, this is it. This is the big reveal. We have all the clues in front of us. Let's put them all together and finally understand why, for an atom of carbon, structure truly is destiny. All right, let's break this down. Take a look at diamond. Each and every carbon atom is covalently bonded to 4 others. This creates a perfect, rigid, interlocking 3D web. Every single connection is a super strong covalent bond, which basically turns the entire diamond into one giant, unbelievably strong molecule. That's why it's so incredibly hard. And notice, all its electrons are locked up tight in those bonds. They can't go anywhere. That's why diamond is an insulator. Okay, now look at graphite. This is so cool. Here, the carbon atoms only bond strongly to 3 others, forming these flat hexagonal sheets, kind of like chicken wire. Now, the bonds within these sheets are strong, but the forces between the sheets, they're incredibly weak. And that is the secret. The layers can slide over each other with almost no effort, which is what makes graphite soft and slippery. Oh, and that fourth electron from each carbon atom, it's now delocalized. It's free to roam between the layers, creating that sea of electrons we talked about. And that's why graphite can conduct electricity. So there you have it. The mystery is solved. Same atoms, same primary type of bond, but a completely different architectural plan leads to wildly different results. It really proves it's not about the ingredients, it's all about the recipe. And this rule that structure dictates property, it isn't just for carbon, it's everywhere. Think about electrical conductivity. Metals, like we saw, conduct electricity whether they're solid or liquid because that sea of electrons is always ready to flow. But in ionic compounds like salts, in its solid crystal form, the ions are locked in place. No go for electricity. But get this, if you melt it or dissolve it in water, those ions are suddenly free to move, and bam, it becomes a conductor. Once again, it's the structure that determines the property. You know, this isn't just some cool piece of chemical trivia. Understanding this fundamental principle is one of the absolute cornerstones of modern science and engineering. It's literally how we build the world around us. You know, there's a line from our source material that just hits the nail on the head. It says, the regular structure of crystals is due to the regular packing of the particles within the crystal. It's that regularity, that deliberate pattern that gives a material its properties. It's an idea that's totally fundamental to chemistry and physics. And this understanding is just incredibly powerful. It means we can't just explain why steel is strong or why glass is brittle. We can actually predict how a brand new combination of atoms might behave before we even create it. This is the very foundation of material science. It's how we design stronger, lighter alloys for airplanes, more efficient semiconductors for our computers, and all sorts of revolutionary materials we haven't even dreamed of yet. So the next time you pick up a pencil or see a diamond, I want you to remember the incredible story that they're telling. It's a story of how simple carbon atoms, arranged in just two different patterns, can create both the softest of marks and the hardest of surfaces. And it leaves us with a pretty exciting question, right? If structure is destiny and we are now the architects, what amazing new worlds will we choose to build?